Storing more than one record per address is known as buckets, and then we'll see about making deletions. When we try to save more than one records in an address, we can tell that particular storage space which can hold more than one record as buckets. So we can tell that the address of that particular bucket is known as a home bucket address. Okay, so it can hold more than one record. Usually in one address only one record can be saved. Now here in a bucket we can save more than one record details. So this is how it looks like. See, consider we are having a key of a record: green, junk, hall, king, land, mark and nuts, and these are the home addresses. Now when we save these addresses or these keys inside a bucket, how will it look like? Now the bucket size here is green, okay, and as green, and here green, you can see that green is having the same home address 30 and junk is also having the same address 30. So it is the two records green and junk will be inside the same bucket address 30. So this is 30. This is the first address, which is 30. Okay, and here it is hall. So we'll see what is the address of hall. It is 31, and so we can tell that the next bucket address 31 will have only one record, and similarly we have empty spaces which can be inserted or used. Now for king it is 33, land it is 33, mark it is 33, and nut it is 33. So 32, this is 32 and this is 33. In 33 you can see that we are having kings, we are having land, and we are having mark. Now in addition to that we are having nut. Now we can tell that nut is not having a space to save it. Okay, so this is nut as an overflow record, okay, or a cluster record which cannot be held by your bucket. Okay, so effective buckets and performance. Now we need to see how much improvement does my bucket address give compared to the known bucket file. Okay, so here for computing the density of my packed file by using a bucket, the main three things which we need to keep in mind is: the first one, the number of addresses n, that is the number of bucket addresses, and the second one is the number of records, that is number of records within a bucket. So in the previous example we have seen that each bucket is holding 3 records, so the B is become 3. Now the number of records, the total number of records is R. So now for finding the packing density, it is R divided by Bn. So consider an example. We are having 750 records to be saved inside 1000 locations without using a bucket. How the packet density becomes 750 divided by 1000, that is 75%. Now by using a bucket, now here I am considering the same situation where I am having 500 location and my bucket size is 2. Okay, so the packing density is R divided by N and B. So it is B is your 2, that is your bucket is 2 size, into N, the total locations, that is equal to 70. So in the performance you can see that it is same. But when we see with an example and compare it with the performance, we can see that the bucket performance try to accommodate, or it gives more room for more records compared to the other addresses which is holding only one record. So here we can see in this one, P of 0, as I have already explained, P of 0 is the address which is holding more 0 records. So the probability with the bucket is 47.2 and with bucket is 22.3. Okay, so you can see the efficiency is more in the case of with buckets because that much of records have been held. Okay, now in the case of P1, that is how much of addresses are holding one record. In this case without a bucket it is 0.35 and here it is 33. Here it is records with 2 records, in the sense bucket holding 2 records. So it is 13 and here it is 0.25. So we can see a large drastic amount of improvement in the case of using a bucket here, and this is in another table which mainly shows how much of improvement we have by using different bucket sizes. If I'm having a packet density of 10, then if the bucket size is 1, the performance is 1.06, and with 2 buckets it's 1.01, with 5 bucket it is 1. In the sense, all of the records are being accommodated. And here if I'm having a packet density of 30, then in the case of using one address, one record, in that case it is 1.21, here it is 1.06. In the case of two records in a bucket and 5 records in a bucket, everything is accommodated, that is 1. Okay, that is what we see if it is using 10 bucket size or 100 bucket size. So we can come to a conclusion that bigger the bucket, shorter the search length. So we are able to access the records as fast as possible when the bucket size increases. So when I see the implementation issue of my using a bucket, we can tell that the hashed file remains the same. Every hashed file mainly can have two properties, that is, it is a fixed length record file, and it is always the accessing of my hash file is done by using RRN. So you know, when I use a fixed length record size accessing, we use RRN for addition, deletion and updation. Here when I do the hashing as well, I use this RRN, so we can tell the hashing is done with the help of my RRN. Okay, so when next concept which you need to see is the bucket structure. How does it look like and how does it work? So we can say that, as I've already told, records in a bucket is having a same bucket address. So we can tell here I'm having a counter for every bucket address. So consider that this 19 is my bucket address and the counter is set 0. In the sense, now none of my bucket or none of my records inside that particular address is occupied. Now here when I see it as 2, in the sense that particular bucket address is containing 2 records, and similarly for the 21 as well, it is containing 2. So this is what the counter tells you, how many number of, or it keeps tracks of the number of records it hold. Now what is an empty record? How do we identify an empty record? Every empty record inside a bucket is filled with a special character slash. Okay, 5 slashes. So this is a special character just filled inside the empty record, which helps us understand that that particular record is empty. So 2 things are used here. Counter is used as well as that special character is used for identifying the empty records. Now for initializing my file for hashing, what are the main things I need to keep in mind? The first one is I need to first create a file with empty records. How many records I need to put into my file? That much number of records, empty records need to be created with the file, and after that one by one I'm going to fill the slots with the record details which I have. So I'm maintaining this procedure. I'm able to save each and every records closer, and I'm able to access it very fast or access it sequentially, and there is less probability that I end up in an error telling that I missed a record. So the next one is loading a hash file. For loading a hashed file, the first method is I need to hash, or I need to do a hashing process over a key and find an address so that I can place the key onto the fixed address, which is found by the hashing method. So that is the first method. And the second one is search for a home bucket address, insert the record and rewrite. So once the record address has been found, there is where I insert my record, and after the insertion is done, I straightway take that hash file, I write it into my file which is on my secondary device. So these are the main steps. Now the problem which I face here in loading a hash file is, if I'm having an empty file and I need to search whether I have an empty bucket, sometimes we end up with an infinite loop. Okay, and the next one is it keeps saving multiple times the same key. So duplicate key is not being handled here. So that is on another case which we need to handle. So the second topic is making deletions. Now when we do deletions, what are the main things we need to keep in our mind? So when we do deletions, we end up having many freed slots. These freed slots, in usual cases, as we have seen before, when freed slots come, we come to a conclusion that there are no more records to the end. So when we do a search, we come across first 2 is being occupied, the third is deleted, and then comes to the fourth. When you keep searching for an example key called X, we search as the first 2. where it is occupied, it is not matching. We go for the third where it is an empty. So we come to a conclusion that only that much record is existing, telling, and we wind up the program. So this is how the program is usually ended. Whenever you have an empty record, we wind it up telling that only that much records are available inside my file. But this happens because of deletion. So we need to use some marker technique so that this can be avoided. So the main marker technique which we use here is known as tombstone, where we insert a special character hash. It is known as tombstones, which tells me that once a record was there but it was deleted. Now whenever we do a search and we come across a tombstone, it means that it is a deleted record and records exist after that. So now the search keeps moving continuously till the end of my file, and if it exists, I am found. If it does not exist, then once we reaches the end of the file, we return telling that it is not found. So this avoids the two problems, telling that it does not hinder the search, it allows us to continue with the search, and it allows us also to reuse the freed space. So whenever we need to do an insertion, the same case, whenever you come across a tombstone, what you have to do, we can make use of that particular address because it is already deleted. Okay, so insertion also you can make use of the same address which is deleted. So this is what we'll explain this with an example. So here this is the example where I have a fixed set of records, and in between this 23rd address record is deleted. When I do a search for searching for key X, I search it here, it is not matching, search here, not matching, not matching, here again it is not matching, and it is empty. So I can usual algorithms have a tendency telling that okay, it is empty file, so it had reached the end of the file and we'd wind up the program. So we don't go here, even if it is an X, we don't find it because our algorithm has been designed like that. So we need to have some solution. That is why we go with the solution called tombstone, which represents the deleted record. Okay, so tombstone is used for represent deleted record. Whenever you come across a deleted record, we turn okay, there are records after it, and the search continues till the end of the file. So once it reaches the end of the file, if the record is found, it is returned, else it returns missed file. So this is how it improves it. Now when you do addition and deletion, what are the main things we need to keep in mind? Okay, the first thing is whenever we do deletion, we need to do a little bit of reorganization, because when we do deletion, we can end up telling that empty spaces are filled up. You can sometimes move the below ones up towards the home address so that the search can be improved, because it happens that whenever deletion has happened, we search, and that the search length keeps moving, or it reaches unacceptable. In those cases, moving the below keys towards the home address will be beneficial, so that you can improve my search length. And or you can use another collision resolution techniques so that my searching time can be efficient and the search length can be reduced. Thank you.